Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So if you are listening to this right now, I want you to just imagine standing in the middle of the Pacific Ocean.
Okay.
And it is the pitch black of night.
Sounds terrifying, honestly.
Yeah. And you are holding just a standard everyday flashlight.
Oh, wow. Okay.
And your task is to find a single specific microscopic organism floating somewhere out there in the water just by wildly waving that beam of light around in the dark.
Which is pretty much impossible.
Exactly. But for a very long time, that is exactly what the search for life outside our solar system has felt like. I mean, humanity has managed to confirm over 6,000 exoplanets so far.
Yeah, over 6,000. It's a massive number.
It is. But until recently, trying to find realistic actual candidates for biology among all those, churning gas giants and freezing rocks, it's just been completely overwhelming. You are basically wandering the cosmos, hoping to bump into an alien microbe.
Right. It's a sheer numbers game.
Yeah. But today, our mission is to understand a monumental shift in this entire field. A completely groundbreaking development that basically takes the flashlight out of our hands, drains the ocean, and hands us a highly specific, mathematically rigorous VIP guest list for the universe.
That's a great way to put it.
Thank you. It's a meticulously curated catalog of exactly 45 potentially habitable rocky exoplanets. It was published in March 2026 by a team at Cornell University.
It's a fundamental paradigm shift. We really need to emphasize the phrase mass discovery versus extreme precision here.
Okay, unpack that for us.
Well, if you look back over the last 20 or 30 years of astronomy, the headline was always about adding another planet to the tally.
Like, we found 50 more today.
Exactly. The sheer volume of discoveries was the story. But this milestone, it's about the complete opposite. It is entirely about filtering the noise.
Filtering out the junk.
Right. The team at Cornell didn't just look at the sky and make optimistic guesses. They took an incredibly vast, almost incomprehensible data set from the European Space Agency's Gaia mission.
That's the data release 3, right?
Yes, specifically data release 3.
Yeah.
And they combined it with the NASA Exoplanet Archive. And by doing that, they applied such rigorous, unforgiving physical and chemical constraints that they managed to just throw out thousands of worlds.
Leaving only the absolute most promising targets.
Exactly. The best targets for future life detection missions.
I want to pause on that phrase, filtering the noise, because if you aren't deeply entrenched in planetary science, it is really hard to overstate how chaotic that noise actually is.
Oh, it's incredibly chaotic.
Right. 6,000 confirmed worlds isn't a list of 6,000 Earths. We are talking about gas giants the size of Jupiter, but they orbit so close to their star that they are just burning at thousands of degrees.
Jupiter's, yeah.
Or we are talking about planets where it literally rains molten glass sideways because the winds are moving at supersonic speeds.
It's a very violent universe.
Just totally hostile environments. And out of all of that chaos, this team, led by Professor Lisa Kaltenegger, whittled the entire known universe down to 45 specific names.
45 very special places.
45 places where you could theoretically look for something looking back. But here's my immediate question. How do you confidently throw away 5,955 planets?
It's a brutal process, honestly.
Right. If we are sitting here on Earth making sweeping judgments about rocks billions of miles away, what is the actual mechanism for saying yes to one and no to 5,000 others?
Well, the very first sweep of that cosmic sieve is based entirely on density and radius. They instantly eliminate anything that isn't rocky.
So gas giants are just out.
Completely out. If a planet has a thick, crushing gaseous envelope like Jupiter, Saturn, or even Neptune, it is immediately off the list.
Because we need a surface.
Exactly. We are looking for a specific type of surface habitability, meaning a solid surface where liquid water could actually pool. But the real heavy lifting of this filtering process, it comes from a concept called the empirical habitable zone.
Okay, I have to jump in here. Because whenever the phrase habitable zone or Goldilocks zone gets tossed around, it always sounds so, aggressively cozy.
Right, like a nice galactic suburb.
Exactly. Not too hot, not too cold, just right. But the word empirical implies we are basing this on hard evidence, right? So what is the actual hard evidence anchoring this zone?
The evidence is our own solar system. That is what makes it empirical.
Oh, I see.
Yeah, instead of just running purely theoretical thermodynamic models, we use our immediate planetary neighbors as the ultimate undeniable benchmark.
So Earth is the baseline.
Earth is obviously the perfect baseline. We know for a fact that liquid water and biology exist here. But to define the inner edge, the absolute too hot boundary, we look toward the sun, to Venus.
Because Venus is a nightmare?
Precisely. Venus represents the extreme limit of a runaway greenhouse effect. And to define the outer edge, the too cold boundary, we look outward to Mars.
Which is essentially a frozen desert.
Right. Mars represents a world with a severely thin atmosphere where water simply cannot exist in a stable liquid state on the surface for any meaningful geological time frame.
I'm going to push back heavily on the cozy aspect of this then. Because if we are using Venus and Mars as our benchmarks, well, both of those planets are technically in our sun's general neighborhood.
They are our literal next-door neighbors.
Right. Yet, if you were to stand on the surface of Venus right now, you would be simultaneously crushed by atmospheric pressure 90 times heavier than Earth's, and you would be boiled alive by temperatures hot enough to melt lead.
It is not a pleasant place.
Not at all. And if you magically teleported to Mars, your blood would boil from the low pressure while you simultaneously froze to death, and you wouldn't be able to draw a single breath of oxygen.
Which is a very grim picture, but very accurate.
So if these two completely dead, violently hostile worlds are the boundaries of this zone, the traditional concept of a habitable zone feels wildly generous. The margins for life must be incredibly, unforgivingly tight.
You've hit on the exact reason why this catalog is such a towering achievement. The margins are razor thin.
I can imagine.
And frankly, the astronomical community has struggled with this exact problem for a long time. Historically, we might spot an exoplanet and say, well, it's roughly in the habitable zone, but our measurements were fuzzy.
We were just guessing, basically.
We were making very educated approximations. But this is where the Gaia mission's Data Release 3 becomes the absolute linchpin of this entire endeavor.
How so?
We cannot know if a planet is walking that impossible tightrope between becoming a Venus or a Mars unless we know exactly, and I mean down to the decimal point, how much energy is hitting its surface.
And to know how much energy is hitting the planet, you have to know exactly what the star is doing.
Exactly.
But how does a satellite like Gaia actually figure that out? If we are looking at a star that is 50 light years away, it's just a blurry pixel of light. How do we move from a pixel to knowing the exact radiation environment of a planet orbiting it?
It all comes down to solving the distance problem through something called astrometry.
Okay, astrometry.
Let me give you an example.
Okay.
Imagine you are holding your thumb out at arm's length.
All right, I'm picturing it.
If you close your left eye and then open it and close your right eye, your thumb appears to jump back and forth against the background of the wall.
Right, yeah, it shifts.
That apparent shift is parallax. Gaia does exactly that, but on a cosmic scale. It measures the precise position of a star in the sky. Then, 6 months later, when Earth and Gaia, which orbits out at the L2 Lagrange point, has moved halfway across the solar system, it measures the star's position again.
Oh, wow.
By measuring that incredibly tiny apparent shift against the distant background galaxies, Gaia calculates the exact geometric distance to that star.
So it's literally just high school trigonometry, just scaled up to billions of miles.
Essentially, yes. But the precision required is mind-boggling. We are talking about measuring angles so small, it's like trying to measure the width of a human hair from miles away.
That is insane.
It is. Now, why does distance matter so much? Because of the inverse square law of light.
Meaning the further away something is, the dimmer it looks.
Right. If you see a star in the sky, you know its apparent brightness, how bright it looks to your telescope. But a star could look dim because it's a small, weak star right next door, or it could look dim because it's an absolute monster of a star that is incredibly far away.
Oh, I see.
Once Gaia gives you the exact distance, you can calculate its true intrinsic luminosity. You know exactly how much energy that star is actually pumping out into space.
Which means the Cornell team finally had the missing variable.
Yeah.
Before Gaia, they might have been guessing, we think this planet gets enough light to be warm. But with Gaia's data, they could say, we know for a mathematical fact that this specific planet receives exactly 1,360 watts per square meter, or whatever the exact number is.
Correct. They calculate the exact stellar energy flux. And if that mathematical flux pushes the planet even a fraction of a percent toward the Venus extreme, they mercifully cut it from the list.
Just totally ruthless.
Very ruthless. If it drops toward the Mars extreme, it's out. They ran thousands of planets through this mathematical formula, and that is how they found the 45 that actually sit perfectly within that mathematical sweet spot.
It really paints a picture of extreme planetary fragility, doesn't it?
It really does.
Imagine being a planet hunter, looking at a distant star, and realizing the planet orbiting it has to walk this absolute tightrope.
A very precarious tightrope.
A tiny fraction too much radiation, the oceans boil off into space, the hydrogen escapes, and you have Venus. A fraction too little, the carbon dioxide freezes out, the atmosphere collapses, and the whole world turns into a giant snowball.
Which is why finding 45 planets that survive that math is staggering.
It is. But as I understand it, the researchers didn't even stop there, did they?
No, they did not.
They looked at these 45 ideal candidates and decided the empirical habitable zone wasn't strict enough. They added an even more unforgiving filter.
They did. For the sake of maximum conservatism, they applied a 3D habitable zone filter.
Okay, what does that mean?
Well, the initial empirical zone we just discussed is incredibly useful, but it fundamentally relies on generalized one-dimensional assumptions.
Like treating the planet as a flat circle?
Basically, it treats the planet almost like a flat, uniform sphere absorbing energy evenly. But reality is infinitely more complex. The 3D filter accounts for atmospheric dynamics, planetary rotation, and how heat actually moves around a three-dimensional globe.
Wow.
When they ran the 45 planets through this hyper-strict three-dimensional gauntlet, the list narrowed down even further to just 24 ultra-high priority worlds.
Okay, so treating a planet like a flat sphere is like, well, it's like looking at a static 2D photo of a house and trying to guess if it's warm inside.
That's a good analogy.
You see the sun hitting the roof in the photo, and you guess, sure, it looks cozy, but the 3D model is like actually walking through the house.
Right.
In the 3D model, you aren't just looking at the sun, you are checking the insulation in the walls. You are kneeling down to feel for drafts under the doors. You are seeing how the air conditioning ducts circulate the air, and you're checking the actual thermostat.
Yes.
A flat photo might show a house bathed in sunshine, but the 3D walkthrough tells you if the living room is freezing because all the heat escapes through a drafty window.
I like the house analogy, but I'm going to complicate it a bit.
Please do.
Because planetary climate is far more chaotic than a drafty window. Imagine that house is also spinning at 1,000 miles an hour.
Okay, now I'm dizzy.
And the heater isn't just a furnace in the basement. It's a massive nuclear reactor hanging in the sky, bombarding the house with radiation. Planets are dynamic, rotating fluid systems. They have varied topographies, massive oceans that act as heat sinks, and swirling atmospheric currents governed by the Coriolis effect.
So how does a 3D model actually simulate all of that? Because that sounds like an unbelievable amount of math.
It requires general circulation models, or GCMs.
Are those like weather simulators?
Exactly. They are essentially the same supercomputer models we use to predict weather and climate change here on Earth. They chop the planet's atmosphere and oceans into a three-dimensional grid, millions of little boxes.
Okay.
Then they calculate the thermodynamics, the fluid dynamics, and the radiative transfer. How light bounces around in every single box, and how each box interacts with its neighbors. What's fascinating here is that this is absolutely critical because of a phenomenon called tidal locking.
Right, tidal locking. I've heard of this. That's when a planet orbits so close to its star that the star's gravity basically grabs hold of the planet's uneven mass and forces it to stop spinning relative to the star.
Yes, the rotation matches the orbit.
So one side is always facing the sun in perpetual daylight, and the other side is staring out into the blackness of space in perpetual freezing night.
Exactly. Our moon is tidally locked to Earth, which is why we always see the same face.
Oh, right.
Now, if you have an exoplanet that is tidally locked to a red dwarf star, a simple 1D or 2D model might take the scorching heat of the day side, average it with the freezing cold of the night side, and spit out a number that says, hey, the average global temperature is 65 degrees. It's perfectly habitable.
But no one actually experiences the average.
Precisely.
Half the planet is an absolute furnace, and the other half is a solid ice block.
Exactly. But a 3D model asks the vital question. How does the atmosphere transport the scorching heat from the day side to the freezing night side?
Oh, so the wind carries the heat.
Does the heat rise at the substellar point, the exact spot where the sun is directly overhead, and flow high in the atmosphere to the night side, creating massive, planet-wide hurricane-force winds?
That sounds terrifying.
It is. Does the ocean have currents that can distribute that thermal energy? If the atmosphere is too thin, it can't transport the heat, and the atmosphere on the dark side might literally freeze solid and collapse onto the ground as snow.
Wait, the air itself freezes?
Yes, atmospheric collapse.
Yeah.
Well, if it's too thick, the heat transport might be so efficient that the whole planet just cooks.
Yeah.
That global circulation of heat absolutely makes or breaks a planet's ability to hold on to liquid water.
And that really makes you stop and wonder about the planet sitting right on the razor's edge of this 3D boundary.
It does.
You could have a world that is, by all accounts, a lush, beautiful paradise. It has flowing water, thick clouds, stable temperatures. But because it's sitting right on the absolute extreme margin of that 3D habitable zone, what happens if there's a slight orbital shift?
A tiny wobble.
Yeah. Or what if there's a minor atmospheric change, like a slight natural increase in a greenhouse gas from a volcano? It feels like it wouldn't take much to tip one of these paradise worlds completely over the edge.
It really wouldn't.
It could trigger a positive feedback loop where the water starts evaporating, water vapor acts as a greenhouse gas, traps more heat, evaporates more water, and suddenly your paradise is just a barren, Venus-like wasteland.
Which tells us a very sobering truth about the universe. Habitability isn't necessarily a permanent state.
It's temporary.
It can be a highly temporary, fleeting phase in a planet's long geological evolution. We know Mars was likely habitable billions of years ago.
Right. It had rivers and stuff.
It had river deltas and lakes. But it lost its magnetic field, the solar wind stripped its atmosphere, and it died. Venus may have had oceans, but the sun grew brighter over billions of years, and it boiled away.
Wow.
Establishing this 3D boundary is a massive leap forward because it strips away the overly optimistic candidates. It leaves us with 24 worlds that have the most robust, resilient potential for maintaining stable, life-supporting climates, despite the chaotic nature of stellar evolution.
So with the list completely whittled down to the 45 overall candidates and the 24 absolute ultra-high priority worlds, I want to talk about the actual names on this cosmic VIP list.
Let's do it.
Who are the neighbors we might actually be visiting, or at least staring at very intensely? Because if you are listening to this and you follow astronomy at all, some of these names are going to jump out at you.
Definitely.
You have Proxima Centauri b, which is incredibly exciting because it's our absolute closest stellar neighbor. It's literally the star next door, and it has a rocky world in the zone.
A fascinating target.
You've got several members of the famous TRAPPIST-1 system. There's Kepler-186, which was a huge deal when it was discovered because it was the first Earth-sized planet found in a habitable zone.
That was a historic find.
And there's LHS 1140b. But beyond the planets themselves, I find the team behind this catalog just absolutely fascinating.
Great group.
You have Professor Kaltenegger, who directs the Carl Sagan Institute at Cornell, but she co-authored this massive paradigm-shifting catalog with an undergraduate student, Abigail Bohl, and recent alumni Lucas Lawrence and Gillis Lowry.
Yes.
We're literally talking about college students and recent grads who are fundamentally writing the roadmap for the future of humanity's space exploration.
It's a wonderful aspect of modern astronomy. It speaks volumes about the accessibility and the sheer quality of the data we now have.
Meaning anyone can look at it.
Essentially, yes. Decades ago, obtaining this kind of data required a lifetime of lobbying for telescope time. Now, massive surveys like Gaia and the NASA Exoplanet Archive are democratized.
That's incredible.
They allow a dedicated team combining seasoned expertise with brilliant, highly motivated young minds to synthesize decades of observations into a precise, actionable database. And it's important to note that they didn't just list these planets arbitrarily.
Oh.
They purposefully categorized them to test very specific boundaries of planetary physics.
Right, because if you just wanted 45 Earth clones, you might miss out on understanding how life works in extreme environments.
Exactly. For instance, some planets on the list have irradiation environments that are practically identical to modern Earth. They are the safe bets.
The easy ones.
But others sit right on the very edges of the habitable zone, specifically chosen so we can test where exactly those boundaries fail. If we look at a planet on the inner edge and see it hasn't turned into Venus, our models need to adjust.
Now, here's where it gets really interesting for me. This is something I genuinely don't fully understand, but it sounds wild. The catalog specifically includes planets with highly eccentric orbits. So instead of a nice, neat, relatively circular path around their star like Earth has, their orbits are stretched out into long ovals.
Highly elliptical.
They are swinging in violently close to the star and then getting flung far out into the freezing depths of their solar system. What on Earth, or rather what out there, would the climate dynamics actually look like on a planet like that?
It would be extreme, to say the least.
If I'm standing on a rocky world with a highly eccentric orbit, am I just experiencing extreme whiplash-inducing seasons? Like a summer where the oceans are practically steaming, followed a few months later by a winter where the entire atmosphere is freezing onto the ground as solid ice.
Orbital mechanics dictate that you absolutely would experience those extremes. According to Kepler's laws of planetary motion, a planet moves fastest when it is closest to its star.
That's periapsis, right?
Yes, at periapsis.
Right.
And it moves slowest when it is farthest away, at apoapsis.
Yeah.
So let's play out the scenario you just described. As the planet swings deeply into the inner solar system, the sudden, violent spike in stellar irradiation could trigger massive, rapid evaporation of surface water.
Oh, wow.
The latent heat of vaporization would pump enormous amounts of energy into the atmosphere, creating incredibly dense, chaotic, planet-wide storm systems, hurricanes that dwarf anything on Earth.
And because it's moving fastest at that close point, that hellish summer might actually be quite short.
Correctly. It whips around the star and then begins the long, slow climb back out into deep space.
And then it gets cold.
Very cold. As it swings back out to the farthest reaches of its orbit, the solar radiation drops off a cliff. All that water vapor that got pumped into the atmosphere. It would begin to condense and eventually precipitate out as global rain, then snow, and perhaps even solid sheets of ice covering the oceans.
That sounds completely inhospitable. Why on earth would the Cornell team put a planet like that on a VIP list for life?
Because studying these weirdos, as we might call them, is vital for understanding the absolute limits of biology.
What do you mean?
Well, life on Earth is remarkably adaptable. We find extremophiles in the boiling, acidic hydrothermal vents at the bottom of the ocean, and we find them locked in the ice of Antarctica.
True, life finds a way.
If a planet has a deep ocean, the sheer thermal mass of that water might buffer the extreme temperature swings. The surface might freeze, but deep down, the water remains liquid and stable.
So the aliens are just hiding under the ice during winter?
Essentially, yes. If we find biological signatures on a planet with whiplash seasons, it completely broadens our understanding of the extreme conditions under which life can persist. It forces us to abandon our Earth-centric biases.
That makes a lot of sense. It's about testing the extremes. And speaking of testing boundaries, the researchers also specifically highlighted some of the oldest known habitable zone rocky planets on the list.
Yes, the ancient ones.
Which, if you think about it from an evolutionary perspective, makes perfect sense. Time is arguably the most important factor in the universe.
It is the most crucial ingredient for complexity. If we connect this to the bigger picture of evolutionary biology, we have to look at our own history. We know that on Earth, life didn't just appear fully formed overnight.
Right.
The Earth is roughly 4.5 billion years old. For the first billion years, it was a hellscape of magma and asteroid bombardments. Once it cooled, simple, single-celled organisms emerged. But they stayed simple for billions of years.
Just floating blobs.
It took an unimaginably long time for cells to develop nuclei, to form multicellular life, and eventually to trigger the Cambrian explosion where complex animals emerged.
So if a planet is relatively young, say just a billion years old, even if it has water and perfect temperatures, we might just be looking at a global ocean full of invisible slime.
Correct. Slime is life, and finding it would be the greatest discovery in human history, but it's not complex life. By actively identifying these ancient rocky worlds planets that age estimates suggest are 6, 7, or even 8 billion years old, the catalog provides us with targets that offer the absolute longest available runway for biology to have taken hold.
That is profound.
If a planet has been sitting in a stable, habitable configuration for 8 billion years without suffering a runaway greenhouse effect or losing its atmosphere, the complexity of the chemistry and potentially the biology could be staggering compared to a younger world. We're looking at environments that have had nearly double the evolutionary time of Earth.
Okay, so we have this incredible VIP list. We have the oldest planets, the weirdest eccentric planets, the most Earth-like safe bets, and our literal next-door neighbors. The map is drawn.
It is.
But if I'm listening to this, my next logical question is, what do we actually do with a list of 45 planets that are trillions of miles away? We have the names, we have the coordinates, but we can't exactly send a probe there.
Not right now, no.
Yet, according to the researchers, this isn't just a fun theoretical spreadsheet. This is a highly practical, literal roadmap for the most advanced technology humanity has ever built or will build in the next century.
Professor Kaltnicker actually summarized the utility of this catalog perfectly. She stated, Our paper reveals where you should travel to find life if we ever built a Project Hail Mary spacecraft.
Oh, I love that book.
It's a great reference. Now, obviously, that is a reference to science fiction. We do not currently possess interstellar spacecraft capable of traveling at fractions of the speed of light to Proxima Centauri or the TRAPPIST-1 system. Sending a physical object there is, for now, impossible.
So what's the practical use today?
The practical reality is that this catalog optimizes observing time for our current and future technological marvels. We are talking about humanity's greatest eyes in the sky.
And when we say eyes in the sky, we are talking about machines that cost billions of dollars and take decades to build. We're talking about the James Webb Space Telescope, or JWST, which is operational right now.
Yes.
We're talking about massive ground-based projects currently under construction, like the Extremely Large Telescope, the ELT, and we're talking about proposed future missions like the Habitable Worlds Observatory, the HWO, and the Large Interferometer for Exoplanets, known as LIFE.
Exactly. And to understand why this catalog is so critical, you have to understand the brutal economics of astronomy. Telescope times is not something a scientist can just casually sign out like a library book.
I can imagine.
It is arguably the most scarce and fiercely competitive scientific resource on the planet.
I imagine every astronomer on Earth has a pet project they want to point JWST at.
They do. Astronomers from all over the world submit incredibly detailed proposals detailing exactly what they want to look at, why it matters, and exactly how many hours of telescope time it will take. The oversubscription rate is massive.
Meaning everyone wants time and there's none left.
Far more requests for time than there are hours in a year. The committees that allocate this time are ruthless. You simply cannot afford to point a $10 billion machine at a random patch of sky and just hope something interesting happens. You need absolute mathematical certainty that the patch of sky you are staring at holds the highest possible probability of yielding a significant scientific return.
So this Cornell catalog acts as the ultimate filter.
Yes.
It's the ultimate trump card in a proposal. You don't have to say, I think this planet might be habitable. You can say, this planet has survived the empirical habitable zone filter, the 3D climate model filter, and it is officially one of the 24 best candidates in the known universe.
It tells these incredibly expensive machines exactly where to look. It equips observers with clear, heavily vetted priorities, and depending on the telescope, they will use incredibly complex techniques.
Like what?
Future telescopes might use direct imaging, where they literally try to block out the light of the host star with a chronograph to see the faint glimmer of the planet itself. Others might use light curve analysis.
Oh.
But most importantly, for our current capabilities with JWST, the catalog provides the perfect targets for a technique called transmission spectroscopy.
I am so glad you brought up transmission spectroscopy because we don't have to wait 30 years for futuristic telescopes to see this in action. The James Webb Space Telescope is up there right now, parked a million miles from Earth, staring down one of the most famous systems on this newly minted VIP list, the TRAPPIST-1 system.
It is actively gathering data as we speak.
But to really appreciate what JWST is finding, we have to unpack how it's actually looking at them, because it's not taking a photograph, is it? It's not zooming in with a super high-resolution lens until it sees continents and oceans.
No, taking a direct photograph of a rocky exoplanet with current technology is virtually impossible. The host star is simply too blindingly bright. It completely washes out the tiny, faint reflection of the planet.
It's like trying to see a firefly next to a searchlight.
Exactly. Instead, JWST is probing the atmospheres of these distant exoplanets using transmission spectroscopy during transits.
Okay, let's break that down mechanically. What is a transit?
The mechanics of a transit are relatively straightforward. From our specific vantage point here in the solar system, the orbital plane of the exoplanet happens to be perfectly aligned, edge-on with us.
So we're looking at it from the side.
Yes. This means that as the planet orbits its star, we can watch as it passes directly in front of the stellar disk. When that happens, the solid, rocky body of the planet blocks a tiny fraction of the starlight, causing a slight dip in the star's overall brightness.
And that dip is how we know the planet is there.
Right. But the magic of transmission spectroscopy happens at the very edges of the planet.
Because the entire planet isn't just solid rock. If it has an atmosphere, there is a tiny, incredibly thin halo of gas surrounding the rock.
Exactly. When the planet passes in front of the star, a minute fraction of the starlight doesn't hit the solid rock. Instead, it grazes the edge of the planet and filters through that incredibly thin sliver of atmospheric gas on its way to JWST's mirrors.
I always try to visualize this because the scales are so insane. I think the easiest way to imagine transmission spectroscopy is to picture yourself trying to guess what color sunglasses someone is wearing.
Okay, let's hear it.
But this person is standing 5 miles away. Obviously, you can't just look and see the lenses from 5 miles away. They're way too small.
Right.
But if you have that person stand directly in front of an incredibly bright, intense searchlight, and that searchlight shines directly through the lenses of their sunglasses and right into your eyes, the beam of light hitting your eyes is going to be altered.
Yes.
If the light suddenly looks tinted green, you know for a fact they are wearing green lenses. The material of the lenses absorbs certain colors of the light spectrum and let other colors pass through.
Your analogy captures the basic mechanism beautifully, but let's make it more scientifically accurate, because JWST's job is exponentially harder than that.
I figured as much.
Imagine that searchlight is constantly fluctuating in brightness. You only get to look at the sunglasses for a few hours every couple of weeks, and the lenses are microscopic.
Yikes. Okay.
When starlight passes through the exoplanet's atmosphere, it isn't just being tinted a single color. The specific molecules floating in that gas, whether it's water vapor, carbon dioxide, methane, or ozone, interact with the light photons on a quantum level.
Wait, on a quantum level, how does a photon of light interact with a molecule of water?
When a photon of light carrying a very specific amount of energy hits a molecule, it can cause the chemical bonds of that molecule to vibrate or rotate. But a water molecule will only absorb a photon if the photon has the exact specific wavelength that matches the water molecule's vibrational frequency. It's like a tuning fork.
Oh, that makes sense.
If it absorbs that photon, that specific wavelength of light goes missing from the beam. So when the rest of the starlight eventually reaches JWST's spectrograph, it gets split up into a rainbow, like a prism.
And there are chunks missing.
Yes. Scientists look at that rainbow and they see dark, vertical bands where light is missing. Those dark bands are a chemical fingerprint. If they see a dark band at a specific wavelength, they can say a water molecule absorbed that light. Therefore, there is water in that atmosphere.
That is just phenomenal. We are literally reading the shadows of molecules cast across trillions of miles of space. And JWST is specifically built for this, isn't it? It doesn't look at visible light like our eyes do. It looks at infrared light.
Yes. JWST is equipped with massive, incredibly sensitive infrared sensors. Infrared is the absolute perfect spectrum for finding these specific chemical signatures.
Why infrared?
The molecular bonds of biologically interesting compounds, things like water, methane, and carbon dioxide, vibrate and absorb light very strongly at infrared wavelengths. The absorption bands in the infrared are deep and clear, making them much easier to detect than invisible light.
And this brings us back to why the TRAPPIST-1 system is the ultimate testing ground for this technology. Because earlier we mentioned how telescope time is fiercely competitive.
Right.
If you want to catch a transit, you have to wait for the planet to actually cross in front of the star. If you are looking at Earth from another star system, you only get one transit a year. You'd have to stare at our sun for a decade to get enough data.
Which nobody has time for.
Right. But TRAPPIST-1 is different. It's an incredibly compact group of 7 Earth-sized worlds, all orbiting a cool red dwarf star just 40 light years away. 40 light years is practically down the street in cosmic terms.
It is remarkably close, which gives us an excellent signal-to-noise ratio. But the most crucial factor is that TRAPPIST-1 is an M-dwarf star, a red dwarf.
Meaning it's small.
It is vastly smaller and cooler than our sun. Because the star is so cool, its habitable zone is pulled in very, very close. The planets orbit tightly. TRAPPIST-1, for instance, completes an entire orbit, a full year in just about 6 Earth days.
6 days. That means it transits in front of the star once a week.
Exactly. Frequent transits mean frequent opportunities for JWST to catch that starlight filtering through the atmosphere. Scientists can't just look at one transit and get a perfect picture. The signal is too incredibly faint.
So they have to add them up.
Yes, they have to stack the data. They record dozens of transits over months and years, overlaying the data on top of each other to amplify the true atmospheric signal and cancel out the random noise. The tight orbits of red dwarf systems make this stacking process feasible within a human time frame.
Which means we actually have real data. We aren't just talking in theories anymore.
No, the data has been pouring in.
JWST has been staring intently at one specific, incredibly promising candidate in this system, TRAPPIST-1. And the data from the observations taken between 2023 and 2025 has been analyzed. And the results are completely upending what scientists thought they would find. They're forcing a total rethink of atmospheric models.
They really are. The recent observations of TRAPPIST-1a are a masterclass in science progressing by the process of elimination.
Process of elimination.
Okay. When you have a rocky world the size of Earth, there are several hypothetical types of atmospheres it could hold. The JWST data analyses have largely ruled out the most extreme scenarios by looking for those deep absorption bands and, crucially, by not finding them.
Let's walk through what they crossed off the list, because if I remember correctly, there were a lot of fears that all these red dwarf planets would just be baked dead husks.
The first major scenario they ruled out was a thick carbon dioxide-dominated atmosphere.
Yep.
The spectral signatures completely disfavor it. This is a massive relief because it means TRAPPIST-1 is not a Venus-like world suffering from a runaway greenhouse effect. If it had a thick CO2 atmosphere, JWST would have seen massive, unmistakable absorption bands at specific infrared wavelengths. They weren't there.
So we can confidently scratch Venus off the list of possibilities for TRAPPIST-1. That's a huge win.
It is a huge win, but the data also doesn't match the signature of a thin, completely CO2-heavy atmosphere either.
Like Mars.
Right, it doesn't have the spectral footprint of Mars. Furthermore, the data has excluded the possibility of a puffy, hydrogen-rich, primordial atmosphere.
Wait, a puffy hydrogen atmosphere? What does that even look like physically? A rocky planet with hydrogen gas?
Well, when planets form out of the protoplanetary disk of gas and dust surrounding a young star, they can sometimes squeak up and retain massive envelopes of hydrogen and helium gas. This is a primordial atmosphere.
Okay.
If a small rocky planet holds onto that hydrogen, it ends up looking somewhat like a miniature gas giant, a mini Neptune.
Oh, interesting.
The hydrogen envelope is very light, so it puffs out far into space. A puffy atmosphere creates a very large, easy-to-see transit signal. But the incredibly flat spectral lines for TRAPPIST-1m tell us unequivocally that this thick, hydrogen-rich scenario is off the table.
So if I am a planetary scientist looking at this JWST data and I realize the atmosphere isn't a crushing hot Venus, it isn't a freezing thin Mars, and it isn't a puffy gaseous hydrogen ball, what exactly is left? If we've eliminated all the extremes, what is TRAPPIST-1m actually made of?
By ruling out those extremes, the data leaves open two incredibly thrilling possibilities. We must be intellectually honest and state the first possibility. The planet might simply be a bare, lifeless rock in space, completely stripped of any atmosphere whatsoever by the intense radiation of its star.
A dead rock. Thrilling for a geologist maybe, but not for someone looking for life. But what is the second possibility?
The second possibility is what keeps astronomers awake at night. TRAPPIST-1m could possess a thinner, secondary atmosphere.
A secondary atmosphere.
This means an atmosphere that wasn't gathered from the stellar nebula during formation, but was generated later by the planet itself, likely through massive geological processes like volcanic outgassing, or brought in by comet impacts.
Like it made its own air.
Exactly. This secondary atmosphere wouldn't be dominated by primordial hydrogen or overwhelming carbon dioxide. Instead, it could be nitrogen-rich, perhaps with traces of water vapor, oxygen, or methane.
A nitrogen-rich secondary atmosphere that basically describes Earth.
Exactly. Earth's atmosphere is roughly 78% nitrogen. Saturn's moon, Titan, also has a thick, nitrogen-rich secondary atmosphere. If TRAPPIST-1m has an atmosphere akin to Earth or Titan, it drastically elevates its status as a primary candidate for astrobiology.
It is just a staggering thought. A rocky planet 40 light-years away, potentially wrapped in a blanket of nitrogen and methane orbiting a red sun. I know we are focusing heavily on this one specific planet, but I have to assume that what we learn from TRAPPIST-1m applies to the rest of the universe, right?
The importance of this stretches far, far beyond just TRAPPIST-1. By eliminating these specific extreme scenarios, the Venus, Mars, and puffy hydrogen models, we are radically refining our foundational models for atmospheric evolution across the cosmos.
Oh, because there's so many of these red dwarfs.
Specifically, yes, for planets orbiting M-dwarf stars, or red dwarfs. And this is critical because red dwarfs are, by a vast margin, the most common type of star in our entire galaxy. Upwards of 70% of all stars are red dwarfs.
70%.
If we want to understand galactic habitability, we have to understand what happens to rocky planets orbiting these specific stars. JWST's work on TRAPPIST-1m is literally writing the textbook on what kinds of atmospheres are physically and chemically plausible in the absolute most common planetary environments in the universe.
But, as with all great scientific endeavors, there is a massive, frustrating cosmic wildcard that threatens to muddy all of this pristine, beautiful data.
There's always a catch.
And ironically enough, the problem comes directly from the very star that provides the light we need to see the planets in the first place. The red dwarf itself isn't just sitting there being a passive flashlight. It's actively fighting us.
Yes, this is known as the red dwarf dilemma. Researchers continually urge extreme caution when interpreting any spectral data from planets like TRAPPIST-1m because of severe stellar activity.
They're unstable.
Red dwarfs are notoriously volatile. They are not calm, steady, burning spheres of plasma like our Sun. They are fully convective stars, meaning the boiling plasma from their core churns all the way to the surface. This creates intense, chaotic magnetic fields.
As they flare a lot.
They are prone to incredibly violent stellar flares, massive eruptions of radiation that can bathe their close-orbiting planets in X-rays and ultraviolet light.
Which sounds terrible for life on the surface, obviously. But how does a flare mess up our data? If JWST is looking for the shadow of water molecules in the planet's atmosphere, how does a star's tantrum ruin that?
It's not just the flares, it's the star spots.
Star spots, like sunspots.
Much like sunspots on our Sun, red dwarfs are frequently covered in massive star spots areas where the intense magnetic fields temporarily suppress the convection of heat, creating patches on the star's surface that are cooler and darker than the surrounding plasma.
Okay.
Because they are cooler, the chemistry of the star in those spots actually changes. Molecules can temporarily form in the cooler regions of the star itself.
Wait, hold on. Molecules can form on the star. I thought stars were too hot for molecules, that everything was just ripped apart into atoms and plasma.
In a star like our Sun, yes. But red dwarfs are cool enough, and their star spots are even cooler, that simple molecules like water or titanium oxide can briefly form in the star's outer layers. And this creates a devastating problem for transmission spectroscopy.
Let me guess. If water molecules are forming on the surface of the star, they're absorbing light before it even hits the planet.
You've hit the nail on the head. This is stellar contamination. When the starlight passes through the planet's atmosphere, it carries the chemical signature of the star spot with it. Earlier in the decade, there were some hints or whispers in the data of methane and water on some exoplanets, which caused massive excitement. But later, rigorous studies came out suggesting that maybe that molecular signature wasn't coming from the planet's atmosphere at all.
It was an illusion.
It was an illusion. The water signature was coming from a massive, cool star spot rotating into view exactly as the planet transited.
So the star is essentially faking the data. It is projecting a hologram of water onto the planet. How do scientists even begin to solve that? If the signature for water looks exactly the same, whether it's from the star or the planet, how do you disentangle the two?
That is the defining question the astronomical community is actively grappling with right now. How do we definitively separate the biological or chemical footprint of a planet from the magnetic temper tantrums of its host star?
It sounds impossible.
It requires incredibly sophisticated modeling of the star's magnetic activity. We have to map the star spots and subtract their spectrum from the planet's spectrum. It requires continuous monitoring.
So it's just really, really hard math.
But we have to be honest. The current data sets, while absolutely revolutionary, are not quite sensitive enough to perfectly untangle the stellar contamination from the planetary signal in every single case. The error bars are still too wide.
Right.
We cannot yet give a definitive 100% certain answer on whether a world like TRAPPIST-1m has that thin gaseous envelope, or if it's just a bare rock reflecting a very noisy, spotty star.
It is such a cruel cosmic irony. The most common stars in the universe, the red dwarfs, are the ones statistically most likely to harbor these rocky planets in tight, observable orbits.
They offer the best targets.
They offer the best chance to stack transit data. But they are also the exact stars that are most actively trying to blind our instruments and confuse our data with their chaotic magnetic fields. It's like trying to listen to a tiny, faint whisper from a planet, but its sun is constantly screaming into the microphone, and the sun happens to be whispering the exact same words you were trying to listen for.
It's maddening.
But even with these stellar tantrums, even with the extreme difficulty of separating the signal from the noise, the sheer combination of the Cornell catalog and JWST's ongoing, relentless mission represents an absolute monumental leap forward. I feel like we are closer than ever to answering humanity's biggest, most existential question.
We truly are. If you look at the arc of this entire endeavor, the field of exoplanet astronomy has fundamentally and irreversibly moved from an era of pure discovery, where simply counting the number of worlds and proving they existed was the primary goal, to an era of deep, rigorous characterization.
We're not just counting anymore.
No, we are no longer just asking, is there a planet there? We know they are everywhere. We are now asking, what is the detailed thermodynamic and chemical makeup of its atmosphere, and what is its true mathematical potential for supporting biology?
And the Cornell catalog is the key.
The Cornell catalog, providing those 45 and the strictly modeled 24 VIP candidates, provides the exact where to look. It acts as the ultimate filter for our most precious resources.
And JWST provides the how.
Yes. JWST, with its incredibly powerful infrared transmission spectroscopy, provides the how to look. Future observatories, the multi-billion-dollar massive machines currently being drafted and built, will take this exact roadmap and build upon it. They won't be flying blind. They will be specifically scanning these prioritized candidates for genuine biosignatures.
And when we say biosignatures, we aren't just looking for water. Water is everywhere. We're looking for things like unusual ratios of water, oxygen, and methane existing in the atmosphere at the same time. Gases that actively react with each other and shouldn't exist together in large quantities for very long, unless something like a massive biosphere of life is actively, continuously producing them to replenish the atmosphere. And if you are listening to this, I really want you to take a second and think about the sheer scale of what we've walked through today. We aren't guessing anymore. We aren't throwing darts at a massive map of the Milky Way hoping to hit something interesting. Thanks to Gaia, thanks to extreme 3D climate modeling, and thanks to relentless data analysis, we possess a prioritized, mathematically rigorous list of 45 actual physical places in the universe where the spark of life might have ignited.
It's a profound thought.
Earth might be a total fluke. We might be a cosmic rarity, an anomaly of geology and timing. Or Earth might just be one incredibly small part of a vibrant, bustling galactic community of living worlds. And for the very first time in all of human history, we aren't just philosophizing about it. We have the map, we have the list, and we have the tools to finally find out.
The transition is complete. The search for life has moved out of the realm of science fiction and theoretical philosophy, and it has become a deeply structured, achievable, data-driven scientific endeavor. It's happening right now, one transit, one photon, and one carefully selected planet at a time.
And as we wrap up this discussion, I want to leave you with a final thought to really mull over. We talked extensively about how the Cornell catalog didn't just look for Earth clones. They specifically highlighted some of the oldest rocky planets in the habitable zone to act as extreme evolutionary test cases. I want you to think about time.
Time is everything.
Life on Earth took roughly 4 billion years to get from simple single cells floating in geothermal muck to complex creatures capable of building space telescopes, mapping the stars, and debating the nuances of red dwarf magnetic flares. Now, imagine a rocky, ocean-filled planet on this new VIP list. A planet that has been sitting in its star's perfect, stable temperature zone, insulated by a thick atmosphere, not for 4 billion years, but for 8 or 9 billion years.
Double the time we've had.
Exactly. If the spark of life took hold in those alien oceans all those eons ago, with more than double the evolutionary runway that life on Earth had, what on Earth, or rather, what out there, would it look like today?